I'm Dr. Martin Khechara from the University of Wolverhampton and the fantastic STEM response team. In this video, I just want to give you an introduction to our chemistry catch-up sessions and also begin to explore some content, some reminders about atoms and ions. So this is what our chemistry catch-up sessions are going to be looking at this time round. I'm going to be doing atoms and ions, as I've just said. We're going to be looking at bonding, looking at chemical equations and calculations, looking at organic versus inorganic chemistry, looking at chemical reactions and equilibria, and then looking at some of the essential maths that's really important for your subject area of chemistry. So, if you want to know more about the fantastic work of the STEM response team or find all of the other revision and catch-up sessions that we've been doing for those of our colleagues starting A-levels or BTEC, or for those people who are considering a career in higher education, you can follow us on all our social networks, but also you can look on our webpage on the University of Wolverhampton website. Okay, so let's start with today's content then. And we're going to look firstly at atoms. And this is a bit of a reminder, hopefully, for everybody out there. Atoms really, as it says here, are some of their parts. They contain three particles. They contain protons and neutrons within the nucleus, and electrons that orbit that particle, a bit like planets around a solar system, in shells. Now, the amount of the different shells sort of determines the size of that atom, and generally, the charge of an atom or an element, if you like this, is zero. And when we lose electrons, we get ionisation and ions are formed, and we're going to look at all of these things. So we can see here, we've got the standard sort of diagram of an atom here. We've got the nucleus, of course, containing our protons and neutrons. And of course, they are most often, of course, in equal numbers. We have the various shells in which the electrons are orbiting. And you can see on this particular example, we've got three shells. And what is a little bit different from GCSE going into A-level and the higher levels of BTEC sort of chemistry you might look at is actually in the past, you might have seen that in shell 2, for instance, that shell can hold 8 electrons. Well, that's true, but however, each of these shells can be split up into subshells. So the second energy shell has 2 subshells, one that holds 2 electrons and one that holds 6. So when we add those two together, of course, we get 8 electrons. And the energy levels, these sub-levels, are called level S, level P, and level D. And of course, when we're actually drawing a particle like this with all its electrons and its orbits, we always start by filling in those bottom shell. And that very first shell can always hold 2 electrons. So we wouldn't be getting very far in chemistry without the fantastic periodic table. And it is atomic structure that allows elements to be arranged logically in that fantastic diagram, sort of first put together by Mendeleev a very, very long time ago. Now, if we look, we've got a symbol for that particular element, and then we've got 2 other figures, and they're labelled Z and A on this diagram here. The bottom number is something called the atomic number, and that is the amount of protons in the nucleus of that element. The second number, which is above, and it's labelled A here, as I said, is the mass number, and that's the number of protons plus neutrons. So if we want to find out the number of neutrons, all we need to do is take Z from A, and then we're left with the numbers of neutrons. And you can see a nice stylized sort of periodic table here. And you can see we've got the groups that go from left to right, and we've got the periods that go down. And that talks about the different chemical properties and reactivities of those elements in the different groups. And for your sorts of studies at the moment, there are some particular groups, as I'll mention in a minute. You can see the first 2 groups, 1 and 2. They are very important for your studies. They're called the S block elements. And then you can see on this, sometimes they're not labelled in this way, but on this particular periodic table, you've got groups 13 to 18. They're actually called the P block elements, and they're very important at the moment for your studies. So we'll concentrate on some of those. So let's remember, all elements in the periodic table are in order of atomic number, and the groups that we have are arranged in similar properties. And as I said, these S block and P block elements are very important for you. And as we move through the periods, the properties change gradually with regards to their reactivity. So if we look at group 1, for instance, we can see from the way it's arranged that lithium is less reactive than cesium, for instance. And if you've ever put any of these metals in water, you'll see exactly what I mean. So when we start to get isotopes, things get a little bit more complicated because the numbers of neutrons can sometimes vary in atoms. Now, atoms of the same element always have the same atomic number, if you like, but different mass numbers, as it says here, are possible due to different numbers of neutrons. And those variations in neutron numbers are called isotopes. And there are a whole variety of elements that do have isotopes. If you look on the periodic table, for instance, you will see some of them. And a really good example is chlorine, because that has got a number of 35.5, showing that it's actually made up of a number of different isotopes of that element. So when we've got lots of different isotopes, and often they're in different relative abundances, the mass number isn't always a whole number, as I've said. I've mentioned chlorine having a mass number of 35.5. And what we've got to remember here, and it's really important, is that some of the isotopes are in different relative abundances. So when we're actually calculating that mass number, we need to take that into account. So you can see here, this is a really good example of how to work out those mass numbers for all these different isotopes. And it is quite easy in as much as all you need is the relative abundancy in a percentage of each isotope, and then you multiply that by the mass of the isotope, and then you sum that, and you do that for each isotope, and then you sum that, and then simply just divide it by 100. And actually you can see at the bottom there the workings for chlorine and how we actually get to this mass number of 35.5. So let's talk about the relative formula, the molecular mass. Now, instead of being just this time being denoted by a big A and a small r in subscript, just like the atomic masses are, the relative formula or molecular mass is a big M and a little r this time. And actually, if you want to calculate this relative formula or molecular mass, what you need to do is just add up all the atomic masses of all the elements in a particular formula. So we could consider CO2. Now, all we've got to do is add together the relative atomic masses of all the constituents of that molecule. So that's nice and easy in as much as we have 1 carbon and the molecular mass is 12. And then we've got 2 oxygens and the molecular mass is, well, the atomic mass is 16. So we can add all them together and we get a relative formula mass of 44.0. Now, for these particular purposes, we can consider molecular mass so similar that it's pretty much the same thing, except we express that in slightly different units. So if we are talking about molecular mass, we need to actually refer to the units as AMUs, or atomic mass units. Now, if you want to find the relative molecular mass, if you like, of a constituent, and you could see this is like a cupboard, you'd find it in any prep room, in any lab, anywhere around the world. You can see there's a variety of different chemicals and bottles here. All you've got to do is just look on the back, and what it'll say is MR, and then it will give you a number of that whole compound or molecule or whatever, right? And then we can use that to do other calculations, because in other catch-up sessions, we're going to be learning about things like molar concentrations. And actually, we need that relative molecular mass to actually calculate molar concentrations of particular reagents. And of course, that's very, very important in all of science that uses these kinds of chemicals. Okay, so occasionally, if we fire enough energy into an element, we can cause the formation of what's called an ion. So that energy actually allows that element to lose an electron from one of its shells, and then it becomes what we call ionised. Now, the energy to remove the first electron from the very outer shell of a particular element is called the first ionisation energy, and it's got a very specific definition, as you can see here. And it is the energy needed to remove one electron from each atom in a 1 mole of gaseous atoms to form 1 mole of gaseous ions. You can see that there. We'll have a little reminder of that in a minute. And the lower the ionisation energy, the easier it is to form an ion. And there's a variety of different things that actually influence that. So the ionisation energy that's needed to actually kick off these electrons is dependent on 3 things primarily. Firstly, the nuclear charge, because the more protons, right, the stronger the actual attraction is from those positively charged particles to the negatively charged electrons. So it's more difficult to shed them. It's easier to ionise electrons that are further away from the nucleus because they're not influenced by the protons quite so strongly. Also, if we have full electron shells on the inside, those shells can actually shield outer electrons from the attraction of the protons in the nucleus. So it's easier for that element to lose them. Now, if we look at trends in the periodic table, because it is magic, the periodic table, and it tells you lots of things if you look at it properly. As we move down periods, down the periodic table, actually ionisation energy decreases. It's easier to actually cause those electrons to be lost. If we move across groups, from group 1 to, as you can see here, to group 0, which is actually helium, then it's harder to remove those electrons, and ionisation energy increases. And this is just a reminder of exactly what I've just said with an example. So finally, let's just consider something called oxidation numbers. Now, if you have seen chemical formula, you will notice that sometimes there's a little number on them. So a really good example of that is iron 2 chloride, or what's called ferric chloride. And you can see the formula there. And actually, when we write it out, you can see we've got these Roman numerals in brackets. And actually, that tells you what the charge is of that particular compound. Now, it is simply the amount of electrons that are donated or lost during a reaction. And actually, that allows us to see the charge on that molecule itself and start to think of how it might react with other things. So this is a rule of oxidation numbers, and these are really good rules just to remember, because they'll really help in your studies later on. So let's think. Non-bonded elements, okay, so things that aren't stuck together, most often have an oxidation number of 0. If we've got identical atoms that are bound together, they often have an oxidation number of 0 too. The oxidation number of an ion that's made of one atom is the same as its overall charge. And for molecular ions, consisting of lots of different things, the overall charge is equal to the sum of all of the oxidation numbers that we see. So from that, we can actually work out quite a lot of things, and these are important to remember. So this is just another example of the periodic table, and you can see that as we move across that periodic table again, because there is so much information in the periodic table, once you understand it, it is a fantastic thing, and you can see the oxidation numbers of the elements in the various groups there. So just a few things to remember then, and so just keep these in mind for when we're moving through some of the other catch-up sessions that you're going to be receiving from the fantastic STEM response team and staff at the University of Wolverhampton. Remember, there are 3 kinds of particle in an atom. Electrons exist in shells, but there's also subshells between those shells. Isotopes have different numbers of neutrons, and the relative atomic and molecular mass are different, but vitally important to understanding how things work. Okay, so I hope you found that useful. Again, lots of reminders for you to be carrying forward into your A-level and BTEC studies, and we hope you find the rest of our catch-up sessions as useful.